Thank you very much for introducing me, and thanks everybody for coming. Very excited to be here and for the upcoming special year. I wanted to give a talk that just kind of, is it sound okay? It's not too loud, it's good, okay. That just sort of introduces a lot of the things that this special year might be about or might be related to, some of the things I'm thinking about. So it's less a talk and more of a ramble, which kind of takes me off the hook for a bunch of stuff. And I want to start sort of very, very grounded and sort of give what I consider maybe the main example problem from which a lot of other research flows through generalizations and necessity and tools developed and such, and then maybe go a little bit into the ether and talk about some things that I don't super understand myself and hopefully we'll learn this year. I drew this picture, which is bad in a few ways. One is that it's incomplete. I just sort of put a cornucopia of things up there. And the other is that it's hard to read, as evidenced by people in the audience telling me so, and me going back and looking myself. But it is what it is. So there's this picture here, which sort of loosely tells you, there's arithmetic, Hodge Theory, Transcendence, and O-minimality, which don't capture everything in full, but they're kind of four big chapters of some kind of story. And I wrote some things in the intersection, some of which I'll talk about in the talk. Okay, so let me start by talking about what an unlikely intersection is. For those who are not familiar, where does this come from? There's a few ways to think about it, but the simplest is if you have a variety X of some kind, and you have subvarieties V and W inside X, and U inside V intersect W. Let me make my U's very distinct from my V's. U inside V intersect W is some connected or irreducible component. Then what you expect is for the codimension in X of U to equal the codimension in X of V plus the codimension in X of W. This expectation is wrong a lot of the time, but naively it's sort of what you would think. This is how many equations cut out V, how many cut out W, and so you would sort of guess that's how many cut out U. And you say that it's unlikely this intersection if instead of equality you get a bigger sign there. So there's sort of some kind of relation between what's defining V and what's defining W. And now, of course, as I pointed out, if you just work in generality, you can set up counterexamples to this all over the place. The idea is to sort of look at restricted situations and then try to classify those counterexamples as well as you can. So more specifically, you sort of want to say that the counterexamples that show up for a number of understandable reasons, and those reasons can be summed up in some finite way in general. Yes. Yes. I heard people whispering. Great. Amazing. Thank you. Less than. It's very unlikely if it's greater than. Okay, so typically, not always, but typically, a situation we might consider is something like we're in some ambient setting, maybe analytic or maybe smooth or something, and V and W could be algebraic for distinct structures. And I'll give some examples of that. And so you get some sort of transcendence statement that you're studying by looking at the unlikeliness of the intersection. And actually, I'll use the board one more time. So one very special case is what's known as a special point problem. And this is a special case where the dimension of V is 0. So V is a point, and then as long as W is not all of X, this is unlikely because most points don't lie on most proper subvarieties, right? Okay, so let me talk about the sort of main example. I want to talk about this very concretely. So this will be the multiplicative group. So I'll just write this as C star to the n. And to start, we'll begin by talking about the special point problem, which is kind of the simplest thing you can talk about. And the simplest incarnation of it is if you take a polynomial, say, you can make it a Laurent polynomial because you're in C star to the n. You can put in complex coefficients or rational coefficients. You can do all sorts of things. You can ask, given this, when is the zero set of f contain, sorry, when does infinitely many pairs of points C and eta such that both of these are roots of unity. And there's a number of ways to motivate this. You can sort of talk about, you have some algebraic relation involving addition and multiplication, and you're looking for that to coincide with purely multiplicative relations. We'll look about another way of thinking about this later on, but this is a straightforward question you can ask. And the answer turns out to be sort of exactly when you would expect when the algebraic relation already expresses some sort of multiplicative dependence. So the answer is when the set contains some set of the form x to the m, y to the n equals a, with a root of unity, and m and n integers. Okay? So the idea being, again, that you have some sort of very specific reason for when this happens. And now before we go, let me try to use this thing and see if it's practical for me. Oh, yeah. Okay. This is the simple case of sort of points and curves, the simplest non-trivial case. Then if you want to go in higher dimensions, is this still visible despite shadow, or do I have to avoid? Okay. In higher dimensions, a typical part of the story is that you have to be careful when asking for infinity of solutions, because you could imagine the following kind of situation. You can imagine having a surface, S, which is some random surface, not expressing any multiplicative coincidences, but S maybe contains a curve, C, which is the diagonal, or something of this form, and then C will have infinitely many points of the kind that you're studying. This shows up in a number of instantiations in this kind of theory. If you're looking for these kind of results in higher dimensions, you have to replace infinitude by Zariski density, exactly to avoid this kind of story. So we'll replace infinitely many by Zariski dense, which I'll write as ZD for short. And then there's a theorem, Lang's conjecture, originally proved by Laurent, but it has like 1,000 different proofs at this point, which says that if you have some subvariety V of C star to the n, and it contains infinitely many torsion points, or points all of whose coordinates are roots of unity, so torsion points in C star to the n, and in fact, not just infinitely many, but as a risky dense set of points in V, then V is of this kind of multiplicative type. Then V is of the form C times T where this Xi is a torsion point, and this T is a subtorus. Of C star to the n. Okay? So you can completely resolve when these kind of coincidences happen, and this is the prototypical special point problem. There's a variety of ways to express this kind of result, and in particular, once you have it and you know that these arms are risky dense, well, then you know there's a risky dense in some smaller subvariety, and you can iterate, and you can rephrase this result by saying there's, all the roots of unity, all the torsion points are contained in finitely many sort of guys of this form, and there's various other ways to say it, but this is the sort of cleanest. Okay, should I try for the sideboards? Let me try for the sideboard and see how that goes. Okay, so now, if one wants to go beyond the special point problem about roots of unity, yes?
Some of us will not see anything if we use the sideboard, because we have.
Okay, great.
I mean, that sideboard should be fine.
This sideboard is good. Sounds good. No sideboards over here. Let me try to use this sideboard and see how that works. Okay, so if we want to go beyond special point problems to these sort of genuine unlikely intersections, in this case, there's a clean way to do it. You can define the rank of a point A1 through AN in C star to the n to be the multiplicative rank. Well, so I'll just say the Z rank of the multiplicative group generated by the AI. So everything generated by multiplying the AIs with various integer exponents. So that rank 0 exactly corresponds to being a torsion point, and then, the higher the rank, the less unlikely the point is. Whoa, okay. So now the sideboards are back in play. Okay, fantastic. Thank you. Very efficient operation. So this is sort of a nice way of summarizing the situation, and we can reinterpret it geometrically by saying that if we have some x in C star to the n, then it turns out that, right here, then x intersect the set of points with rank at most m is nothing but the union over all torsion cosets T of dimension at most m of x intersect T. Because having rank m exactly means that you can express all but m of the coordinates in terms of the other ones multiplicatively, which exactly means you're in a torsion coset of this form. Okay, and so this will be unlikely, right? The moment that the codimensions here sum to more than n. So if you work out what that translates to, the expectation, sort of naively, is that x intersect T is empty if the dimension of x plus m is less than n. So again, you have these sort of naive expectations. They're of course false, and they're easy to make counterexamples to. For example, you could just take T, take a large dimensional subvariety of T, and pick x to be anything containing that large dimensional subvariety. The idea is if coincidences happen, they're sort of forced. They're engineered by us. There's only finitely many at a time. And so the conjecture in this case, and this is a special case of Zilber-Pink. But in this case, it is due to Bombieri, Masser, and Zanier. which is that if the set of points with rank less than or equal to, sorry, I think I made a mistake again. Maybe I didn't. Less than or equal to, no, maybe I didn't. To the is less than the codimension of X. Yeah, that's what I want. If this thing is Zariski dense in X, see, no, the points which are supposed to be empty, if they exist so much, there's a Zariski dense, then X is contained inside some torsion coset. T is a proper torsion coset. Okay. And there's a bunch of partial work done towards this conjecture due to Habeger and Bambier-Mastrezanier and other people as well. I'm not gonna list all of them, but this conjecture is still very much open and something that I hope maybe this year people can have some ideas about, because I think there's a lot of interesting stuff to be done there. But okay, this, in my mind, is sort of the prototypical, at least arithmetic, unlikely intersection question, and then a whole bunch of other work is done by taking this sort of setup and then moving it on to other settings, as I will describe later on. Are there any questions about this setup here so far? Okay. So now that I have these boards free for my use, let me talk about another perspective. A transcendence perspective, which is often a sort of clearer perspective to think about in this world, because you're allowed to sort of forget about arithmetic and you can sort of count dimensions geometrically in a more naive fashion. So the transcendence story is the following. We have the exponential function from C to T star to the n, which sends a point Z. Put a hat here to denote Z1 to Zn. Not quite to the exponentials, but I'm going to put a 2 pi I in front of every coordinate for sort of the standard number theoretic reasons that I want my monodromy to have an integral structure and not 2 pi I times an integral structure. And then the question in the transcendence world, which you can understand from model theory maybe most cleanly, but just directly as well, is just exactly how transcendental is this map. Right, so what do I mean by that if you haven't seen this before? Well, it's easy to show that E is transcendental in the literal sense of not being an algebraic map for the sort of natural algebraic structures here and here, but you can be more or less transcendental, and you can measure that by the interaction between the algebraic structures between these two guys with the map E. So for example, here's a relation. If you look at E of x plus y, you get E of x times E of y. Check it, it's true. And one way of saying that is if I let gamma A be the graph of addition, and I let gamma M be the graph of multiplication, then E of gamma A equals gamma M. Right? So I can say that without reference to addition and multiplication, just by saying here's an algebraic variety here, which is sort of algebraic in both worlds. We call this bialgebraic. The image here is also an algebraic variety, up to some openness and component issues, which we're not going to dwell on too much. If I just send this up, it would be a disaster. I should have done it earlier. Okay. All right. So more generally than that, if I look at E of any Q linear, so the slope is Q, affine subspace, inside c to the n, so linear relations with rational coefficients, but maybe the constants are not rational, I get a torus coset. Not necessarily a torsion coset, but a torus coset. So for example, any point is a coset of the trivial torus, which is just the identity. And then there's a theorem you can prove in this case, which is that all bialgebraic sets are of this form. So I'll say torus cosets on the GM side. So as far as the transcendence goes, if you're measuring things which are literally algebraic in the same world, it's just these guys. But okay, the story is sort of not over there. You can sort of measure intersections beyond between the algebraic structures beyond just literally identities. You can ask, when do algebraic relations on one side imply algebraic relations on the other side? And that's exactly asking these kind of unlikely intersection questions. So you have other theorems here. There's a theorem dubbed X-Lindemann, which says if you have algebraic varieties, V in C star to the n, and W in C to the n, such that E of W is contained in V, when can this kind of thing happen? Well, it can happen through bialgebraics in the obvious way, and the theorem is that's the only way that that happens. So there exists a torus coset V which contains S, yes, such that W is contained in E inverse S. So the only way to get containments is take something algebraic in both worlds, make it bigger in one world and smaller in the other. And you have the other theorem in the other direction. Oh, there's only two here. Okay. Let me go back to this board then. I feel like when I first started giving talks in Germany, and I had to use their sort of water sponge erasers, you feel like you're making a mess everywhere. And I feel similar here. Everyone gets to slowly see me. And that, okay. Okay. All right. So then following up on that, you have a stronger theorem, X-Shanuel. Technically, this is weak X-Shanuel. And it's called X-Shanuel because it's a theorem of X acts, but inspired by conjectures of Shanuel and number theory, which are also very interesting, which we're not going to talk about in this talk for lack of time, which says that in the same setup there, if you have U contained in E inverse of V intersect W, so this is the kind of situation we started talking about in this board before I erased it. You have an unlikely intersection between things that are algebraic between two different worlds. You want to understand what's going on. Then there has to be some bialgebraic responsible. So then there exists a torus coset S in C star to the n, such that U contains is contained in E inverse S. And if I look at U contained in E inverse of V intersect S, intersect W intersect S. So if I zoom in on sort of S, which is bialgebraic for both worlds, then this is not unlikely. Sort of saying if you have an unlikely intersection, well, you were sort of just looking at the codimension in the wrong space. It was really all inside some smaller space to begin with. Okay, so note that, I guess, in this world, torsion cosets is just a torus coset which contains a root of unity. Okay, so this transcendental picture that we're talking about doesn't quite capture torsion cosets because it can't see arithmetic. It can't tell arbitrary torus cosets from the torsion cosets we sort of care about. But if you were to work over Q instead of just over C and bring in the arithmetic of Q bar, then you would see it also in this picture, and that's where a lot of the sort of power comes from. Okay. I'm sorry? It would still work, yeah. You would need the transcendence theorems to take them into account, but you need them anyways. Mm-hmm. Are you just saying the power series for either the 2 pi i's? You can do it either way. You have to be careful about the fact that the pi is there, but you can phrase the action for this function just as well. Yeah, we can talk about it afterwards, but you can do this way as well. Mm-hmm. Oh, yes, unlikely. That's right. It's too high up now, but yes, if U is contained inside there, is unlikely. I guess the way I wrote it actually is correct even without that, because if it's not unlikely, I can take S to be C star to the N. So I assume I thought of this earlier, on purpose did this. But no, I forgot. You're right. I should have assumed unlikely. Okay. So what I want to do is I want to give the fastest sketch of the proof of the one of the modern proofs, the one involving the current sort of paradigm, the most popular paradigm, with what's known as the P-Lassagne method of Lang's conjecture. This is not the original proof, and the original proof is worth studying because it has ideas, p-adic ideas that I think could really be useful these days. But let me focus on this proof. Is Lang's conjecture still on the board? No, it is not. But okay, so suppose, yes. Yes. 100%. For sure. For sure. I'm extracting the pieces I want to talk about. You're right. A lot of these theorems that I'm quoting actually do a bit more, or a lot more. So suppose V intersect C star to the N torch, roots of unity is Zariski dense in V. So there's sort of three ingredients. One of them is lower bounds for Galois orbits, which is oh, did I not write that one down? Ah, that was one of the big ones. It should be in that. Let me put it in because I want it in here. Lower bounds for Galois orbits is in this and this and this one. So lower bounds for Galois orbits. I mean, this is all a little artificial, but I decided to put it in this little corner. O-minimality and transcendence and arithmetic. Okay. So lower bounds for Galois orbits. And in this case, this ingredient is very simple. Given a root of unity, or an n-tuple of roots of unity. We need a way to measure its complexity. I'm going to measure it by the order, which power of it first becomes 1. Then if you look at the Galois orbit of it, you look at the size of this grows like a power of its order, d. This is not a hard arithmetic input, but it's very powerful in this context. In fact, you can say what delta is. Delta is, sorry, not depending on delta, greater than this. I think in this case, you could take delta to be 1 over n, but I'm going to leave that as a question. Over n minus epsilon. But there's some delta which does that. The point being, if you have a variety v, and in principle, v could be defined over the complex numbers, but this reduces to looking at the arithmetic situation very quickly because roots of unity themselves are arithmetic. If it contains 1 torsion point, it suddenly contains a whole bunch of them. And that's kind of the starting input to most of these proofs. Not literally all of them, but most of them. It's very hard to do something with 1 torsion point. Once you get a bunch, all of a sudden you get coincidences, and that gives you power. 1 second, just let me finish this one thing. Go ahead. What do I mean by? Oh, lower bounds for Galois orbits. Yeah. Second ingredient is point counting, which is now we have v containing many roots of unity, which means E inverse of v, its inverse image under the exponential, contains many rational points. And this is where a lot of the power comes from in this method, is that you have these truly transcendental functions which take arithmetic values at all of these rational points. And somehow that creates a tension which you can then exploit. That's the clearest intuitive way that I think through which I understand this method. So if this contains many Q points, you show that E inverse of V contains algebraic curves, or varieties more generally. In fact, most of the Q points around have to be contained inside these algebraic varieties. There's just no way to make functions, to make sets, reasonable sets, contain lots of Q points besides having algebraic varieties around, which is not to say that algebraic curves or varieties all have many Q points, right? Many of them don't, Mordell conjecture and stuff like that. But if you do, then you have to be algebraic, is the point. And the third ingredient is transcendence. So literally the X-Shanyo result, in fact, the X-Lindemann result that we just wrote down over in that board. So X-Lindemann implies that V contains torus cosets, but they contain roots of unity, so therefore torsion cosets. Okay, then there's bookkeeping and there's work and stuff, but this is the idea. This is how you get torsion cosets around, and upgrading this enough, you prove the Lang conjecture. Okay, so that's the idea. And one note I want to give is that in many cases that are around today still unsolved, in particular the Bombieri Masser-Zanier case and also Zilber-Pink for Shmur varieties, this lower bounds for Galois orbits is often the missing ingredient. So this is not I haven't looked up the latest like literal implications theorems of if this then that, but if you could establish lower bounds for Galois orbits and it has precise meanings in various incarnations in a variety of settings, you could then go a long way or just literally prove the special point problems at the very least, or even the atypical intersection questions. Okay, so that's how the strategy goes. So let me say a word about the point counting. And we have two of the world's experts in the point counting here, Jonathan Peele and Gal Beniamini, at least in this aspect of it that I'm going to talk about. And before I give the results, let me just give some basic definitions. To count anything, we have to order it. So we need a notion of height. We define the height of an integer just to be its absolute value. We define the height of a rational number in lowest form to be the max of the top and the bottom. And we define the height of a bunch of rational numbers just to be the max of the height of each one individually. So it's just a very sort of rough notion of size for the kind of theorems we're going to be talking about. The precise notion here, it doesn't matter. If you sort of add them instead of taking maxes or even multiply them all, that would all still be fine. There are cases, usually when you deal with different varieties at once, when this kind of roughness is not sufficient, and you have to be very careful about your notion of height. Been a lot of work, for example, by Yuan and Zhang, defining sort of very precise heights for line bundles and stuff. But in this case, what we're talking about here, those kind of nuances don't come up. And then finally, if you have an x inside Rn, you just define this counting function to be the number of points in x that are rational of height at most t. So this sort of counts some asymptotic of how quickly x gets rational points as you go up. Okay, so what is the theorem? A theorem. I've lost track of board, so I'm just going to go over here. I feel like someone should give a class on board work, like which boards to use when. Or maybe I'm the only one here who has this problem. But I often find myself getting overwhelmed by the amount of choice, and it becomes kind of nonsensical. Okay, so the theorem I'll give the version due to Pila-Wilke. If you have x in R to the n, and x is nice, which we'll define in quotes in a minute. So this will mean definable in an O-minimal structure. And I'll phrase it in this way, which might be a mistake. If n of xt does not grow subpolynomially in t, so if this is not true, I don't know how to write it with a logical not operator. So if you have an infinite sequence of t's, for which you do have sort of polynomially many points, then x contains algebraic curves, semi-algebraic curves. So if you aren't familiar with the semi here is meant to allow inequalities of real polynomials as well as equalities. It's a much more natural category from sort of a model theoretic point of view. If you want to do like Chevalet's theorem over the reals, you want the semi-algebraic category. Sorry? Yes. Oh, sorry, much more is stronger. So yes, sure, defined over Q. And in fact, you can actually say that most of the semi-algebraic things account for most of the rational points. You can get more precise, but I just want to not overwhelm people. And in fact, there's an important upgrade recently due to Beniamini and his collaborators. So if you deal with a sharp O-minimal structure with sharp derivatives, so Be careful around Gao. He'll burst your bubble. Then you can replace subpolynomial by a power of log, which is much stronger and is legitimately an important improvement in many of these number theoretic applications. Okay. Sorry? That's right. That's right. Because 2 to the x, this is sharp, and even this is sharp, though not because of 2 to the x. If you just deal with O-minimal structures, you cannot improve this t to the little of 1. Let me check how I'm doing on time. Okay, I was given a very stern warning that we have to be out by 2:35, so I'm going to honor that. Okay. Nope, that's a mistake. Okay. Okay, so what is O-minimality and why does it come into play here? Can you guys see this board now, or is this blocking? It's okay? Okay. Sorry?
The very edge is invisible, but we can guess it.
Okay. Well, I can move off the very edge. That's okay. O-minimality. There we go. Okay, so a class of functions, a class of sets is better than functions. In Rn, for every n and one, for every n at once. So define a minimality, you got to talk about sort of everything all at once. In every R to the n, you allow some sets, and then that whole thing becomes O-minimal if it is closed under Boolean operations. So you can do your quantifier stuff, you can project, you can multiply, you can intersect, you can do all that good stuff. Basically anything you can write down in first order logic. And the sets in R, just in one dimension, are finite unions of intervals. Okay, there's a few variations on how to define it, and I'm not going to do it precisely. Yes, projections and etc. stuff like that. Did I just say Boolean? Oh yes, sorry. Closed under Boolean and quantifiers. I apologize. So any class of functions that you can sort of, whatever formula you write down in them with just first order logic. So in particular, you aren't allowed to take countable unions or reference the natural numbers. Whatever sets you define in one dimension are going to stay simple, right? So you might wonder, why is this interesting? Well, because if you add something crazy in R squared, then you can define some crazy formula with it, eventually project back down to one dimension, maybe you'll get something bad. So in particular, many things aren't in O-minimal structures. So like y equals sine of x is not in, and the way the terminology is definable, in any O-minimal structure. Why? Because if it were, well, you'd intersect it with the x-axis and you would get a countable discrete set, which is not a finite union of intervals. Okay, so periodic functions in particular are not definable in O-minimal structures, but a lot of other very reasonable sets are. So before let me go over here. I think I want a bigger board for this. I want to leave this up. Maybe just let me go to the other thing up there. Oops. Oh, this is not going to work anyway. It's going to be blocked. Okay, I'll use this one then. So before I give you examples of O-minimal structures, because it's not clear that any exist, a priori, what's sort of good about them? So properties. So if X is definable in an O-minimal structure, it has a bunch of properties. So for example, it has finitely many path-connected components. So the topology doesn't get too crazy, and in particular, if X consists of points, it consists of finitely many points. So you don't have to worry about infinite intersections. You get a CK cell decomposition. Decomposition for every case. Even though it's not in the definition, somehow you get some level of smoothness for free. And in sort of the nice cases, you have analytic cell decomposition. Most of the cases that number theorists tend to work in as well. And the way to summarize this is, I would say, is you sort of get the rigidity and finiteness properties of algebra, a lot of them at least. And in fact, sharp O-minimal structures get you even more because they kind of bring in the idea of the degree of a variety into this world. But you're allowed many more functions. So that's kind of the idea. Algebra is too small to handle some functions that we want, like logarithm, the exponential, various modular functions, functions in Hodge theory, etc. And this is a way to deal with them without going to the full world of, for example, holomorphic functions or something like that, where you get a set of singularities, you get all sorts of bad behavior. This is kind of a tame world. The only caveat is when you work with O-minimal structures and you build things from them, you're only ever allowed finite unions or finite operations. So something being locally true always means there exists some finite cover where something is true. In particular, when defining sheaves of any kind or defining manifolds, you're only ever allowed finite covers whenever working with O-minimal structures. Okay, so examples of these things. So the smallest example, and I'm not going to give references here as to who proved what, just to go quicker, but the classic one, the smallest one of interest to number theorists is R-alg, which consists of all semi-algebraic sets, which you can think of as take real algebraic varieties and then do first order logic with them and see what you get. Do you get all sorts of crazy stuff? If you were to work with complex algebraic varieties, you have Chavalet's theorem, which tells you only get constructible guys by doing this. In the real case, this is not true. You can get like the closed disk, which is not a real algebraic variety. But it turns out that you only ever stay in the world of semi-algebraic sets, which is an O-minimal world. Okay, then you have various enlargements of this. You have Rexp, which is you take R-alg and you throw in the graph of the real exponential, and you generate whatever you can, which is a lot. This turns out to be O-minimal as well. You have Rn, which is a much bigger O-minimal structure than Rx, even though it's not strictly bigger. It's bigger in some, not quite cardinality, but basically sense. Because you take R-alg and you throw in all over-convergent functions. So you throw in all graphs of power series on disks, which converge on larger disks. Okay? And then you see whatever that generates. So it's a cool fact that, in fact, neither of these contains the other. This one has no chance of containing this one, because, come on. This one you might think contains Rx, but in fact it doesn't. You can show that any graph, one-dimensional graph of a function inside Rn is polynomially bounded. You can't get a growth rate faster than a power of x, whereas in Rx, of course, you have the exponential function. And in fact, this is the smallest O-minimal structure containing something that grows faster than polynomials. So it's a cool little characterization of the exponential function. Regardless, you have these two, and then you can smoosh them together, and this is still O-minimal, and this is not formal. So there is no largest O-minimal structure. If you take two O-minimal structures and join them together, you're not guaranteed to get an O-minimal structure. So there's real content in proving this. And this turns out to be, so this is not true anymore. What I'm about to say is less true after Gal's work. But for a long time, and still for a lot of applications, this is really the only O-minimal structure you need to know. It's enough to do Hodge theory, it's enough to do Shmurov variety, it's enough to do everything where I know there's something O-minimal. Rnx is the place to work. The reason I say that it's no longer the best place to work is because this is not sharp O-minimal. Is this how you write sharp O-minimal? Just like, yeah, okay. This is not sharp O-minimal, okay? But inside here, if you work with like Pfaffian functions, for example, some kind of, you allow certain kinds of restricted differential equations, and here I'm talking out of my field of expertise, then you get something sharp O-minimal. And so you have to restrict your functions a lot more, but this is basically where we end up working. And it turns out that these days, at least, I mean, there's a variety of proofs of everything. The field has moved quite a bit, but where did it go? Oh, did it leave? Oh, it left. Okay, well, I wrote three ingredients. I wrote the lower bound for Galois orbits, the transcendence, and the point counting result. And all three of those have proofs that involve O-minimality. And in the most general, not the most general, but the more general case of Shmurov varieties, at some point, those were the only proofs that were known were involving O-minimality for all three of those ingredients. So somehow, this sort of method, which was developed for this field of unlikely intersections, has since gone on to have a life of its own, has many other applications now, for example, as applications in lattice point counting and uniform Manin-Mumford, due to the work of Gao and Halbeger and Dimitrov and others. It's become sort of a standard method in number theory. Okay, any other questions before I move on yet again? So I did promise I'll fail, and I will in fact fail. So I can see that I'm running out of time. So let me hint at generalizations. The main thing to keep in mind in this field, I really do maintain, is sort of the multiplicative group case. All of the ingredients you can see have simpler variants in the multiplicative case where everything's super concrete and all the proofs can be translated to sort of often more complicated proofs, but still proofs in this setting. So this is the place, the Ax-Shanuel, the Transcendence results, and this arithmetic is the key canvas on which to work. But generalizations, what I wanted to talk about is you have, so we have the torus, we have tori, so we have sort of GM to the n, which gives us Lang's conjecture and the Glasgow Ax-Shanuel and stuff. You can work, instead of in a torus, you can work in an abelian variety, A, where, instead of C to the n covering C star to the n, you have C to the n covering the complex points of A, where you multiply a lattice of twice I guess C to the GO, right, for a G-dimensional abelian variety. And instead of Lang's conjecture, here the analog becomes the Manin-Mumford conjecture. And you have the same Ax-Shanuel theorem here, the same transcendence results as you do here, literally with torsion cosets, only now you work with abelian subvarieties instead of tori. Of course, the methods are somewhat different for these proofs, but they can be uniformized, and it's kind of the same story. Then you have the world of Shimura varieties. And the classical one to think about is, well, not the classical one, but the one to think about is AG, so the moduli space of principally polarized abelian varieties, which looks similar, but it's sort of a non-abelian picture of this, where you have a certain space. Here it's Ziegel upper half space, which consists of symmetric G by G matrices with positive definite imaginary part. And this covers AG. And the covering group now, instead of just being a lattice group, is SP or PSP 2G of Z, the Z points of the symplectic group. And once again, you have an algebraic structure here, a semi-algebraic structure here, and one here. And you can talk about Q points here or arithmetic points here. So you have all the same transcendence machinery set up. And you have the same extranual results. And here you have Andre Oort is the analog of the special point problems. And of course, the Zilber-Pink conjecture sort of here and here, very much analogous with this and very much not solved. And what I wanted to spend some time selling you guys on, but I don't have time, is that all of these are examples of mixed, if you want to include these two cases, Hodge structures or moduli spaces of mixed Hodge structures. So do I just want to say stuff in words or? Yeah, I'll say stuff in words because I want to get to Nonabelian Hodge theory. So all three of these cases, you can talk, here it's extensions of Z0 by Z1, here it's of Z0 by the H1 of the abelian variety, and here it's sort of weight one Hodge structures. But you can define this sort of object, a Hodge structure or a mixed Hodge structure, which you can assign to any complex variety, and it gets a bad rap because it's kind of complicated. But it's just a linear algebraic object, and its moduli spaces give you sort of a vast variety of things which encompass these examples, and they're better to work with because, well, in many ways they're better to work with because one, they have certain advantages over working in these concrete cases. It's a Fibonaccian category, you can tensor stuff, but more importantly, they encompass a lot more examples. If you take any sort of geometric family, you get a geometric variation of Hodge structures. And they simplify things because the sort of analog of the torsion cosets with the torus cosets, you can describe purely Hodge theoretically in terms of having certain Hodge vectors and such. So it's a world where I think a lot of benefit could be given just by taking these stories and translating them to Hodge theory, especially the arithmetic part is sort of left undone. But okay, I don't have time to talk about that, so I will accept that. And instead, in my remaining 2 minutes, leaving 3 for questions, I will talk about non-abelian Hodge theory very, very quickly, not justifying either of these words, except for maybe theory, which is just a setting that I think a lot of questions remain in that I want to introduce to be able to talk about. It's a very simple setup. If you take X to be, let's say, a smooth projective variety over C, then you have a Riemann-Hilbert correspondence, which goes from local systems on X to flat bundles on X. So given a local system, you can make a flat bundle by declaring these the flat sections. And given a flat bundle, you can get a local system by taking analytic solutions. And it turns out that these both give you, if you look at rank n local systems, These both give you algebraic structures. M and Betty and M and Deram. And the Riemann-Hilbert correspondence gives you an analytic isomorphism between them. And this is a setting that I just wanted to bring up because very little is known here. This is exactly ripe for the kind of transcendence questions we've been asking and the arithmetic questions. And there's a little bit of work, but largely this is unexplored in this context. Okay, so I'll stop here. Thank you very much for listening to me ramble.
Are there any questions?
Last bit. I mean, in the other cases, the O-minimality timing the cusp.
Yeah.
Yeah, the problem's much more basic.
No, well, that's one question. I mean, one of the earliest questions you can ask is this definable in an O-minimal structure? And we don't know that. I think, I'm not even sure what we believe. I'm not even sure what we am referring to. But there's at least some kind of conjectures you can make here about O-minimality being present somewhere. And then you can, of course, ask, even without O-minimality, about like which sets are bialgebraic between these two. Obviously, if something comes from geometry, it's bialgebraic just because of the functoriality, but there could be other ones.
Any other questions? No, fine.
You could consider, you mean if you get rid of the projective assumption, then you can talk. Yes, you can. I've only considered them enough to find them a little scary so far, but that is very interesting for sure, especially in reference to like the period conjecture. Irregular singularities become interesting because you get the exponential function in two different ways, and you got to figure that out. But yes, that's very interesting.
All right. If you have other questions, you should just find Jacob sometime this year. All right. Thank you again.